Welcome to CodeWhisper Podcast, Episode 4. Today we're taking a deep dive into what I think is a really foundational world. Algorithms and data structures. We're building on some fantastic material you've provided us, straight from a free codecamp.org tutorial. It's given us this incredible stack of sources to really work with. Our mission for this deep dive really is to shortcut your way to being truly well-informed about these crucial concepts. We're going to unpack what they are, why they matter, how to evaluate their efficiency. I think most importantly, how they're actually used, in the real world to solve everyday problems and power the tech you rely on constantly. By the end, you'll hopefully have a clear roadmap for how to think about and apply these powerful tools. So yeah, let's unpack this.
It's an exciting journey, definitely. And it's about far more than just, academic theories. We're looking at the core ideas that make modern software even possible. When we talk about an algorithm, it's not just the sequence of steps you kind of come up with on the fly. Over time, the entire field of computer science has identified these established, incredibly efficient ways to solve particular problems. Algorithms really represent this deep, proven body of knowledge. Think of it like a meticulously crafted recipe, maybe honed over years, for a very specific culinary task. This recipe guarantees a good outcome every single time, assuming, of course, you follow the steps correctly. It's not just doing something, it's doing something in a known, optimized way.
That's a great analogy, a proven recipe. And it brings up an immediate practical benefit, doesn't it? If you're unaware that a well-vetted, highly efficient solution already exists for a problem you're facing, well, you might spend ages trying to invent one yourself. And frankly, the likelihood is that your homemade solution won't be as efficient or as thoroughly vetted as these established algorithms. I mean, imagine trying to build a new search engine from scratch without ever having heard of existing, incredibly sophisticated search strategies. You'd just be reinventing the wheel and probably doing it rather poorly. Which leads us right into why understanding algorithms truly matters.
Exactly. And beyond just, avoiding reinventing the wheel, there's a second, or arguably even more important component, algorithmic thinking. This is the ability to look at a complex problem and skillfully break it down, break it into distinct, manageable steps. And once you have those steps, you can then identify the most suitable algorithm or data structure for each individual part of the task. This skill is incredibly valuable. It's precisely why it's so highly sought after in big tech interviews.
Ah, right. The interviews.
Yeah. Interviewers aren't just looking for someone who can memorize and, regurgitate a specific algorithm's code. That's not the point. What they truly care about is whether you can take a seemingly insurmountable problem, dissect it into its core components, and then pick the right tools, the right algorithms or data structures to solve each distinct piece. It demonstrates genuine problem-solving prowess, not just memorization.
So it's not just theory then, it's kind of like your software's crystal ball. Algorithmic thinking lets you predict, before you even write a line of code, if your application will grind to a halt under pressure or scale effortlessly to millions of users. It gives you a deeper understanding of complexity and efficiency in programming, helps you anticipate how your code will perform in different situations, and this is absolutely crucial for building robust and scalable applications. I mean, think about Facebook. Imagine if when you searched for a friend, the app just put up a spinning activity indicator and said, come back in a couple hours.
Nobody would use it.
Exactly. We wouldn't use it, would we? Companies make search as fast as possible because it really matters for user experience, for business operations. And these aren't just for social media either. Efficient algorithms are used in things like DNA sequencing.
Oh, absolutely. Critical applications.
Allowing researchers to understand and combat diseases faster by processing just vast amounts of genetic data.
So when we define an algorithm, it's not just some casual suggestion for how to do something. It has to adhere to very specific principles to be considered, robust and verifiable. What are the absolute non-negotiables? What makes an algorithm fundamentally good and reliable? Our first guideline has to be that an algorithm must have a clear problem statement. You need to precisely define what the input is and what the desired output should look like when the algorithm is done. No ambiguity allowed. For a search algorithm, maybe the input is a series of values and the output is the location of a target value or, an indication that it wasn't found.
Okay, clear problem statement. Got it. And once you have that clear problem, the algorithm itself needs to contain a specific set of instructions in a particular order. We really need to be crystal clear about the sequence, right? The order they're executed in. Like if you're defining linear search and you tell a computer to move sequentially to the next value, before you tell it to compare the current value to the target, Your algorithm would completely miss it if the first value was the target. Computers don't have common sense.
Not at all.
They do exactly what they're told, precisely in the order they're told. So specific order is incredibly important.
Right. And building on that, the third guideline is that each step in your algorithm definition must not be a complex one. It needs to be explicitly clear. This means you shouldn't really be able to break down any of the steps into further subtasks. Every step needs to be distinct, kind of atomic. You can't define linear search as just search until you find this value because that's too vague.
Too high.
Exactly. It needs to be broken down into much more granular steps like compare current to target, move to next, and so on.
Makes sense. Next, an algorithm simply must produce a result. Seems obvious, but
crucial.
if it didn't, how would we ever know if it works or not? To verify correctness, you absolutely need an outcome. Even if you're using a search algorithm and the value isn't found, that not found message is a valid and informative result. As long as the algorithm can consistently produce some understandable result, we can analyze its behavior.
And finally, maybe two related points. An algorithm absolutely must complete in finite time. It cannot potentially run forever. Imagine if we asked someone to find a specific book in the world's largest library. Without a clear ending condition, they might wander indefinitely.
You'd never know.
You'd never know if they succeeded or failed. An algorithm that could run indefinitely is not useful because you'd never get a verifiable outcome. And perhaps most critically, for the same input, a correct algorithm must always produce the same output. Consistency.
Consistency, that's key for reliability.
Absolutely. If you put in the same list of numbers and search for the same value, it should always give you the same position every single time. If it varies, then something is inconsistent in its definition. It's not reliable.
Okay, that clarifies the bedrock of what makes an algorithm. Robust software depends on this. So with these principles in mind, how do we measure how good an algorithm is, especially when we're comparing different approaches to solve the same problem?
Right. When it comes to algorithms, there are two fundamental measures of efficiency we look at: time and space. First, time complexity, often just called running time. This measures how long an algorithm takes to complete its task. It's a universal measure. In that guessing game example from your source, where John and Brittany searched for a number, it was measured by the number of tries or turns they took.
Fewer tries meant faster, more efficient time-wise.
Exactly. Fewer tries, more efficient algorithm in terms of time.
And then there's the other side of the coin, space complexity. This sounds more computer-specific.
It is. This deals with how much working memory or extra storage beyond the input data itself an algorithm consumes on the computer. In the early days of computing, memory was incredibly scarce and expensive, so this was paramount.
Yeah, you had like kilobytes to work with.
Right. But it remains crucial today, especially for large-scale data processing, where even a small per-operation memory footprint can add up to huge demands when you're dealing with massive data sets.
So it's a balancing act.
It really is. A truly useful algorithm effectively balances these two measures. You might have a blazingly fast algorithm, time-wise, but if it demands more memory than your system actually has available, well, it's practically unusable.
Right. It doesn't matter how fast it is if it crashes the machine.
Precisely. It's that delicate dance between speed and resource consumption.
Okay. And when we evaluate an algorithm's efficiency, whether it's for time or space, you mentioned we always analyze its performance in a specific scenario.
Yes. We always analyze its performance in the worst-case scenario.
Why the worst case? Why not average or best?
Because the worst case provides an upper bound. It tells us the algorithm will never perform worse than this. It eliminates surprises and ensures reliability under the most challenging conditions. Like if you're searching for a name in a massive list.
The worst case is it's the last one, or not there at all.
Exactly. The name is either the very last item in the list, or it's not in the list at all. By designing and analyzing for that worst case, you guarantee a certain minimum level of performance, no matter what the input data looks like.
Okay, that makes sense. Plan for the worst, hope for the best. So to really understand this performance scaling, we often visualize it, right? We plot the algorithm's running time, like the number of operations against n, the size of the input data. What does that graph really tell us?
That visualization reveals the algorithm's growth rate, sometimes called its order of growth. Understanding how an algorithm's performance scales as n gets very, very large is absolutely critical. It's essential for designing efficient systems that can handle real-world data volumes, which are often enormous. It shows you how that recipe we talked about performs as you dramatically scale up the ingredients. Does it stay manageable, or does it explode?
Okay, that's a great foundation. With that in mind, let's deep dive into some specific algorithms, starting with maybe the most straightforward one, linear search, also called sequential search or simple search. How does this one work?
Linear search is exactly what it sounds like. It's straightforward. You start at the beginning of a list or a range of values, and you sequentially compare each item to your target value. You just keep going, one by one. You continue this process until you either find a match or you reach the very end of the list without finding it. Imagine you're in a bookstore looking for a specific book. If you use linear search, you'd start at the first shelf, look at every book's cover or spine. Potentially very tedious. If it's not the one, you move to the next book and the next and the next until you find it or you've literally checked every single book in the store. Simple concept, yes, but for a large store, it could take a very long time.
And that leads directly to its efficiency, or maybe inefficiency, doesn't it?
Indeed it does. In the worst case scenario, remember, that's what we focus on, where the target is the very last item, or it's not in the list at all.
You have to check everything.
You have to check every single item. So if there are n items in the list, it takes n operations and comparisons. This type of performance is known as linear time. And in that big O notation we mentioned, it's represented as ON.
O of n, linear.
Its performance scales directly, linearly, with the size of the input. Double the number of items, you roughly double the maximum search time.
Okay. Simple, predictable in its scaling, but maybe not the fastest. Now let's look at something dramatically different. Binary search. This is where it gets really interesting, I think. But first, there's a crucial prerequisite for this one, right?
Absolutely critical. Unlike linear search, which works on anything, binary search absolutely requires the input list to be sorted. For example, it needs to be in ascending numerical order or alphabetical order. Without this fundamental precondition, the algorithm simply won't work correctly.
Why is sorting so essential?
Imagine if your list of numbers was unsorted, say 10, 2, 14, 5, 8, and you started in the middle. Maybe the middle value is 14, and your target is 5. Binary search logic would say, okay, 5 is less than 14, so discard everything from 14 onwards.
But 5 is in the first half in that unsorted list.
Exactly. If the list isn't sorted, the value 5 could be anywhere, even in the discarded half. So sorting is absolutely non-negotiable for binary search to function reliably.
Okay, so assuming our list is sorted, how does it work? It's magic. How does it get so fast?
Right. So instead of starting at one end like linear search, you first determine the middle position of your sorted list, let's say index mid. Then you compare the element at that middle position, list mid, to your target value. If they match, fantastic. You're done. You found it. You return the position mid. But if they don't match, here's where the power comes in. If the middle element is smaller than your target, because the list is sorted, you know your target must be in the upper half. So you can immediately discard the entire first half of the list, everything from the beginning up to and including the midpoint.
Wow, just throw half away.
Just like that. Conversely, if the middle element is greater than your target, you know the target must be in the lower half. So you discard the entire second half, everything from the midpoint onwards. Your new search area is now confined to just one half of the original list.
And then you just repeat.
You just repeat the process. Find the new midpoint of the remaining half, compare, discard half again. You keep doing this on the new, smaller sublist. You continue until either the target is found or the sublist is reduced down to nothing, which means the target wasn't in the list to begin with.
That sounds incredibly efficient, like the dictionary example, right? Open in the middle, then the middle of the remaining half.
Exactly like finding a word in a physical dictionary. You don't start at page 1, aardvark, and read every word.
Yeah.
You open roughly to the middle, see if you're too early or too late in the alphabet, then jump to the middle of the relevant remaining section. You narrow it down incredibly fast.
And real-world apps use this.
All the time. This is how search engines, like, say, Facebook finding a friend, can feel instantaneous, even with billions of users. Imagine if Facebook used linear search. It would put up that spinning indicator and maybe tell you to come back in a couple of hours.
Yeah, that wouldn't work.
It wouldn't work at all. And it's not just social media or dictionaries. Binary search is used in critical scientific applications too, like DNA sequencing. Researchers use it to quickly find specific genetic markers in vast amounts of data, helping them understand and combat diseases much faster.
The efficiency of binary search sounds truly impressive then, especially for these huge data sets.
It really is. With each step, each comparison, it effectively discards half of the remaining data. This means the number of operations grows very, very slowly as n, the input size, increases. Let's put some numbers on it. If you have, say, 1,000 items, a linear search could take up to 1,000 operations in the worst case. but binary search. On a sorted list of 1,000 items, it takes around 10 operations, max.
10 versus 1,000, that's huge.
It's a massive difference, and it gets better. If n is 100,000 items, linear search is 100,000 operations. Binary search still only takes about 17 operations.
Wow, 17.
17 comparisons, roughly. This incredible efficiency is known as logarithmic time, represented as O log n in big O notation. It's often called sublinear because its growth curve on a graph is dramatically flatter than linear times curve. It scales incredibly well.
It sounds like binary search is always the better choice then, right? Given that efficiency. Is there ever a scenario where you wouldn't reach for it first, assuming you could sort the data?
That's a great practical question. Not always, actually. While binary search is significantly faster for the search part, you have to remember its crucial precondition. The data must be sorted first. Sorting data itself has a computational cost. We'll talk about sorting costs later, but they aren't free. So for very small lists, maybe just a handful of items, the overhead of sorting might actually take longer than just doing a quick linear search.
The setup cost might outweigh the search benefit for small n.
Exactly. Or consider lists that are constantly changing items being added or removed frequently. If you use binary search, you have to resort the list very often, which could be inefficient. In those specific cases, a simple linear search might, perhaps surprisingly, be more performant overall because it has less setup or maintenance overhead.
So the key takeaway is understanding the context.
Absolutely. Understand the problem context, the size of the data, how often it changes, and how often you need to search it. Then you balance the cost of sorting versus the benefit of faster searches. No algorithm is a silver bullet. It's always about choosing the right tool for the specific job.
That makes perfect sense. Trade-offs everywhere. Okay, so we've touched on big O notation a few times, ON for linear, O log n for binary. It seems like this universal language for talking about algorithm efficiency. Think of big O not just as some mathematical notation, but maybe as your early warning system for scalability. It tells you, sometimes counterintuitively, how a seemingly small increase in data can transform your Zippy app into a brazen, frustrating experience. But what exactly is it, and why is it so crucial for developers?
Right. Big O notation, represented by that uppercase O, is a theoretical notation, a mathematical way to describe the complexity or efficiency of an algorithm. Specifically, it describes it as a function of the size of its input, which we usually call n. It's really a way to simplify all the complex performance data points and timing graphs we might generate into a concise variable, a standard classification. It's crucial because it allows developers to quickly compare different algorithms that solve the same problem and, critically, understand how their performance scales as the input size grows really large. And importantly, big O notation typically describes the upper bound of an algorithm, meaning its worst-case performance. That O actually comes from order of magnitude of complexity. It gives us the dominant term of the growth rate.
Okay, so it's about the growth rate, the scaling, especially in the worst case. And does big O apply universally, or are there specific contexts? Like, can I compare a search algorithm's big O to a sorting algorithm's big O?
You raise an important point there. Complexity is always relative, and we usually compare algorithms within the same problem domain. It wouldn't make a lot of sense to directly compare the efficiency of, say, a linear search algorithm to something like a merge sort algorithm, using big O in terms of which is better overall, because they're designed for fundamentally different tasks. Search finds things. Sort orders things.
Right, comparing apples and oranges in terms of purpose.
Exactly. You compare search algorithms to other search algorithms, sorting algorithms to other sorting algorithms. You're looking at how different approaches to the same problem scale.
Got it. Okay, so we're looking at how algorithms scale as n, the input size, gets really big. Let's walk through some of the most common big O runtimes you'll encounter, maybe starting from the most ideal and going towards the least practical. What's the absolute best case scenario?
The absolute best is constant time, written as O1. Constant time means the algorithm's runtime remains the same. It's constant, regardless of the input size n. It takes the same amount of time whether you have 10 items or 10 million items. This is the most ideal scenario you can achieve.
What's an example of O1?
A perfect example is reading a value from a list or an array if you already know its exact position, its index. For instance, accessing my list 5. This is a single, fixed operation. Calculate the memory address and grab the value. The total size of the list simply doesn't impact how long that specific operation takes. In Python, even getting the length of a list using len is typically O1 because the list object stores its size.
Okay, O1, the dream. Next up, the incredible efficiency we saw with binary search. Logarithmic time, O log n.
Right, O log n. With logarithmic time, as the input size n grows very large, the number of operations increases extremely slowly. Its growth curve on a graph flattens out dramatically, making it highly efficient for large data sets. That's why we often call it sublinear.
And the classic example is binary search.
Binary search is the poster child for O log n. Every time you double the input size, the number of operations required only increases by a constant amount, typically just one more comparison. This happens because the algorithm repeatedly cuts the problem space in half, rapidly narrowing down the possibilities. It's a fantastic scaling property.
Then we have the one we saw with linear search, linear time, ON.
Yep, ON. In linear time, the number of operations grows directly and proportionally with the input size n. If n doubles, the number of operations roughly doubles in the worst case. Linear search is the prime example, where you might have to check every single item. Really, any algorithm that requires sequentially checking or processing every single item in a collection, once like finding the maximum value in an unsorted list by looking at each one, will typically have an ON linear time complexity.
Okay. Moving up the scale of computational costs, things start getting a bit more expensive. We have quasi-linear time, ON log n.
ON log n. Quasi-linear time describes a runtime that's somewhere between linear ON and quadratic. It's worse than linear, but much better than quadratic, especially as n gets large. The notation, ON log n, tells you that for every element in the input, that's the n part, the algorithm performs an operation that scales logarithmically, that's the log n part. Merge sort, which we'll definitely explore in depth shortly, is a prime example of an efficient sorting algorithm that has an ON log n worst-case runtime. Many efficient sorting algorithms fall into this category.
And then getting significantly more expensive, we hit quadratic time, ON2.
Where quadratic time means the number of operations grows as the square of the input size n. This typically happens when an algorithm involves nested loops over the input data. For example, if you have n items, and for each of those n items, your algorithm needs to perform another n operations, like comparing it to every other item, you're looking at n times n, or n squared operations in total.
Like nested loops comparing everything to everything.
Exactly. Imagine creating a grid or a map where you need to visit every single XY coordinate pair. If the grid size is n by n, you'll have n2 cells to visit, n2 operations. Many basic, perhaps simpler sorting algorithms, like selection sort or bubble sort, can have a quadratic worst-case runtime, which makes them pretty impractical for very large data sets. The time just blows up too quickly.
And just to be aware of it, although maybe less common in intro examples, you can go even higher, like cubic time, ON3.
Yes, absolutely. ON3 is when operations grow as n to the power of 3, perhaps involving 3 nested loops. While less common in the algorithms we typically focus on initially, it's worth knowing that algorithms can exist at this level of complexity, and they quickly become computationally prohibitive even for moderately sized inputs.
So O1, O log n, ON, ON log n, ON2, ON. These seem to fall under a broader umbrella.
They do. We can group them into a general category called polynomial runtimes, often written as ONVARC. This category includes constant, where K0 kinda, linear K1, quadratic K2, cubic K3, and so on, where K is some fixed constant value. Algorithms whose runtimes are bounded by a polynomial function of n are generally considered efficient in theoretical computer science, meaning they are likely solvable in a practical amount of time for reasonable input sizes. They're widely used in practical applications.
Okay, so polynomial is generally considered good or feasible, but then there's the other side. The truly astronomical, often impractical category, factorial or combinatorial runtimes like ON.
Oh, yes, ON. This is where the number of operations grows astronomically fast. N factorial n is n multiplied by every positive integer less than it down to 1. So 3 is 3, 2, 1 equals 6, 4 is 4, 3, 2, 1 equals 24, but it explodes quickly. 10 is over 3 million, 20 is enormous.
Wow.
The classic example often cited here is the traveling salesman problem.
Right, finding the shortest route to visit a set of cities and return home.
Exactly. A naive approach might try to check every single possible route. For just 4 cities, there are n 1.2 unique routes, which is manageable. But for an n value of, say, 20 cities, the number of possible routes is immense. For 200 cities, forget about it. It would literally take longer than the age of the universe to solve with such a brute force algorithm.
So completely impractical for anything but tiny inputs.
Almost always, yes. Algorithms with factorial runtimes are almost never practical for large n. However, studying these types of problems is still important. It helps in developing general optimization strategies, approximation algorithms, finding a good enough solution quickly, and in recognizing problems that are fundamentally hard or potentially unsolvable within realistic timeframes. It adds to find the limits of practical computation.
Wow. That's a fantastic overview of the Big O landscape. So we've built this strong theoretical foundation. We understand what algorithms are, why they matter, the principles they follow, and how we measure their efficiency using Big O. Now let's try to bridge the gap. Let's see how these powerful ideas are actually represented in code, maybe using Python primarily, just to gain a deeper, more practical understanding. And you mentioned earlier, when we look at an algorithm, it often has multiple steps, right? Some fast, some slow. How do we determine the overall complexity? You used a triathlon analogy.
Yes, that's an excellent question to revisit, and it's crucial for analyzing real code. Well, individual steps or lines of code within an algorithm might have different complexities. Some might be constant time O1, others linear ON, maybe some logarithmic O log n. The overall big O complexity of the entire algorithm is determined by its least efficient step, the bottleneck. Think of that triathlon again. You might be a phenomenal swimmer, setup maybe, and cyclist O log n speed. Truly world class. But if your running leg is slow, say ON, if that's your weakest component, then your overall race time will be dominated by your running time.
The slowest part dictates the whole thing.
Exactly. No matter how much you optimize your swimming or cycling, your slowest part dictates the overall process time, especially as the distance n increases. Similarly, in an algorithm, the most computationally expensive step, the one with the highest order of growth in the worst-case scenario, dictates the big O complexity of the entire algorithm. The faster parts become negligible by comparison as n gets large.
That makes it so much clearer. Focus on the bottleneck. Okay, so let's apply that to our first algorithm again, but this time looking at code. Linear search, implemented in Python. How does that function typically look, and what's its overall complexity based on its steps?
Right. Our linear search function, let's call it linear search, input list target, is usually quite intuitive to write. It takes a list of items and the target value you're looking for. The core logic typically uses a for loop, something like for I in range. Inside this loop, it checks if input list is target. If a match is found, it immediately returns the index, which is I. If the loop finishes entirely without finding a match, the function might return none or maybe -1 to indicate not found.
Okay, so what are the costs of those steps?
Well, operations like getting the length input list are usually O1 in Python. Accessing an element by index input list is also O1. The comparison equals is O1. Returning a value is O1. However, the for loop itself is the dominant factor. In the worst case, target at the end are not found, that loop must iterate through all n elements of the list.
So the loop is OM.
The loop itself introduces the ON component. Because that's the least efficient part, the overall complexity is dictated by it.
Making the whole function ON.
Exactly. This iterative nature, the need to potentially touch every element, leads to an ON linear time complexity for the linear search function. It's simple code, highly effective for very small lists, and like you said before, you've probably written code just like this many times without necessarily thinking, linear search algorithm.
Yeah, definitely. Okay, now for the more efficient one, but with that precondition. Binary search, implemented in Python. Let's look at the iterative version first. And I'm assuming that crucial precondition still applies here in the code, right? The input list must be sorted.
Absolutely. That's the first and most critical point to reiterate, maybe even put as a comment in the code. The input list must be sorted for this binary search implementation to work correctly. If you pass an unsorted list, you'll get incorrect results.
Okay, assuming it's sorted. How does the iterative Python code handle that divide and conquer logic of binary search? And what makes its implementation O log n?
All right. The iterative function, say binary search, sorted list, target, usually starts by setting up pointers or indices to define the current search range. It initializes a first index to 0, the start of the list, and a last index to len sorted list, 1, the end of the list. It then enters a while loop. The condition is typically while first off last, meaning the loop continues as long as there's a valid search range, at least one element. Inside the loop, the first step is to calculate the midpoint index. Usually midpoint equals first plus last. We use floor division to ensure we get an integer index.
Okay, find the middle.
Then compare the value at the midpoint, sorted list midpoint, to the target. If they match sorted list midpoint target, we found it. Return midpoint. If the midpoint value is smaller than the target, sorted list midpoint target, we know the target must be in the upper half. So we update first equals midpoint plus 1. This effectively discards the lower half. If the midpoint value is greater than the target, sorted list midpoint target, we know the target must be in the lower half. So we update last midpoint 1. This discards the upper half.
Adjusting the first or last pointer shrinks the search window.
Precisely. And the loop continues with this new, smaller range. If the loop eventually finishes because first becomes greater than last, it means the search range is empty and the target wasn't found. In that case, we return none or -1.
So what about the complexity here? The operations inside the loop seem fast.
They are calculating the midpoint, accessing the list element sorted list midpoint, doing the comparison, reassigning first or last. These are all O1, constant time operations.
But the loop itself is the key.
Exactly. The key is that each iteration of the while loop effectively halves the size of the search space, last first, because the work done per iteration is constant O1, but the number of iterations required grows logarithmically with the input size n, since we have the problem each time. The overall complexity is dominated by the number of iterations.
Which gives us O log n.
Which gives us that highly efficient O log n logarithmic time complexity for iterative binary search. The loop's effect on the dataset size defines the overall complexity, even though the operations inside the loop are individually O1.
That makes sense. The number of times you run the fast operations depends logarithmically on n. Okay, that iterative approach is clear. But that brings us to a super powerful and sometimes, maybe mind-bending concept in programming, recursion. What exactly is it? It feels different from just using loops.
It is different. Recursion is a fundamental programming concept where a function solves a problem by calling itself as a subroutine. It's a way to approach problems by breaking them down into smaller, self-similar subproblems. The idea is you solve a complex problem by assuming you already have a way to solve slightly simpler versions of the exact same problem. The analogy often used is imagine you have that very complex math problem in a textbook. The instruction says, to solve this, first solve the simpler version on page 50.
Yeah.
You go to page 50 and it says to solve this, first solve the even simpler version on page 20.
Keep going deeper.
Exactly. This continues until you reach a page with a problem so basic, so trivial, you know the answer directly. Maybe the answer is 1. You then take that answer 1, go back to page 20, use it to solve that problem. Maybe the answer is now 3. And you take 3, go back to page 50, solve that problem, maybe 10. Finally, you take 10 back to the original page and solve the initial complex problem.
So the function keeps calling itself to get the next piece of the puzzle working its way down and then builds the solution back up.
Precisely. It calls itself to solve smaller instances, eventually hitting a simple case it knows how to solve directly, and then uses those simple solutions to construct the solution for the larger instances.
So if a function calls itself, how does it ever stop? That sounds like it could easily lead to an infinite loop. What are the essential components needed to make recursion work safely?
That's the crucial question. Every correctly written recursive function must have 2 key components. First, 1 or more base cases. These are the absolutely essential stopping conditions. Under a base case condition, the function returns a value directly without making any further recursive calls. This is what prevents the function from calling itself indefinitely and causing an infinite loop or stack overflow.
The trivial problem you know the answer to.
Exactly. The simplest version of the problem that doesn't require further recursion. The second component is the recursive case. This is the part of the function that does call itself. But critically, in the recursive case, the function must call itself with a smaller or simpler version of the original problem. Each recursive call must move the problem state closer and closer to meeting one of those defined base cases. If it doesn't get simpler, it'll never stop.
Okay, base case to stop, recursive case to make progress towards the base case. Let's see how that looks with the recursive binary search in Python. How would we define its base cases and recursive cases?
All right. Let's define recursive binary search. Maybe sorted list target. We need base cases first. The first one is failure. If the maybe sorted list we receive is empty, len maybe sorted list equals 0, it means the target wasn't found in the previous step's sublist. So we return false. This handles the scenario where the search space has shrunk down to nothing. The second base case is success. We calculate the midpoint of the current list. If maybe sorted list midpoint means target, then we found the target. We return true.
Okay, empty list means fail. Found at midpoint means succeed. Those are the stops.
Right. Now for the recursive cases, where we call ourselves again, we calculate the midpoint. If maybe sorted list midpoint is less than the target, we know we need to search the upper half. So the function makes a recursive call. Return recursive binary search. Maybe sorted list midpoint plus 1. Target. Notice the use of Python's list slicing here. Maybe sorted list midpoint plus 1 creates a new sublist containing only the upper half, and we pass that smaller list to the recursive call.
Passing a smaller version of the problem.
Exactly. And if maybe sorted list midpoint is greater than the target, we need to search the lower half. So it recursively calls itself again. Return recursive binary search. Maybe sorted list midpoint target. Again, list slicing creates a new, smaller sublist, the lower half, to pass to the next call.
And that return keyword before the recursive call is important, right?
Critical. It ensures that the final result, true or false, from the innermost call that hits a base case gets passed all the way back up the chain of recursive calls to the original caller.
Okay, that makes sense. So the number of times a recursive function calls itself before hitting a base case, that's called its recursive depth. You mentioned earlier that there are some practical implications for using recursion, particularly in Python. What's the real difference between iterative, loop-based, and recursive solutions in practice, especially regarding memory or space?
Yes, that's a really important practical consideration. While both iterative and recursive solutions can solve the same problems and often have the same time complexity, like O log n for both our binary searches, they can differ in other ways. In Python, iterative solutions, the ones using while or for loops like our first binary search, are generally favored for performance and resource usage. Recursive solutions, while sometimes more elegant or mathematically intuitive for certain problems, like tree traversals or, arguably, merge sort, come with specific implications in Python. First, Python has a default maximum recursion depth. It's a safety limit, often around the 1,000 or maybe 3,000 calls, depending on the system, to prevent runaway recursion from consuming all system memory. If your recursive function calls itself too many times without hitting a base case, it will halt execution with a recursion error, maximum recursion depth exceeded, often referred to as a stack overflow error.
So deep recursion might just stop working.
It might. But perhaps more relevant to typical complexity analysis is the impact on space complexity. Python, unlike some other programming languages, does not typically implement an optimization called tail call optimization or tail call elimination.
Tail call optimization, what's that?
It's an optimization that some languages or compilers can perform. If the very last action a function takes is to call itself a tail call, the optimizer can potentially reuse the current function space on the call stack instead of allocating new space for the recursive call. This can make certain types of recursion very memory efficient, essentially turning them into loops under the hood.
But Python doesn't do that.
Generally, no. Standard Python interpreters don't perform tail call optimization. This means that for functions like our recursive binary search, where a new slice of the list is created and passed into each recursive call, each of those recursive calls consumes additional memory on the computer's call stack. The stack keeps track of active function calls. So while the time complexity of our recursive binary search is still O log n, its space complexity in this Python implementation is also O log n. The depth of the call stack grows logarithmically with the input size because we need to store the context for each pending recursive call.
So the recursive version uses more memory than the iterative one in Python.
Yes, typically. The iterative version usually has O on space complexity, just needing a few variables like first, last, midpoint, while this recursive version using slicing has O log n space complexity due to the call stack depth and potentially the memory for the slices themselves, depending on implementation details.
That's a crucial distinction, especially if memory is tight or n is huge.
It is. And it's important to know that other languages, like Swift or Scheme or some functional languages, do implement tail call optimization. In those languages, a properly written tail recursive function can achieve O1 space complexity, making recursion a more viable and efficient option. So understanding this language-specific nuance is vital if you work across different programming environments.
Okay, that's a fascinating deep dive into how algorithms actually work in code, the iterative versus recursive trade-offs, and the importance of language specifics like tail call optimization. Now, let's pivot slightly. We've been talking a lot about algorithms, the recipes, but recipes need ingredients organized in certain ways. Let's introduce the companion concept. Data structures. Why do we even need different data structures? Don't programming languages just provide built-in ones like lists? Why bother with others?
That's a fundamental question, and the answer gets to the heart of efficient programming. While programming languages do provide useful built-in data structures, like PyCon's list, which we've been using extensively, or dictionaries, no single structure is a perfect fit for every single problem. Each data structure is specifically designed and optimized to solve a particular type of problem most efficiently. It's about matching the structure to the task. For example, arrays, which Python lists resemble, excel at very fast access to elements if you know their position. But as we'll see, they can be slow for other operations like inserting or deleting items in the middle. Other structures, like linked lists, might be better optimized for frequent insertions and deletions at certain points, but they trade off that fast random access capability. It's all about trade-offs, tailored to the problem's access patterns and modification needs.
So it's about choosing the right container for the job, based on how you need to use the data inside it. What exactly is a data structure then, beyond just being a collection of values? What does it define?
A data structure is much more than just a collection. It rigorously defines three key things. First, how data values are organized and stored in the computer's memory. Are they next to each other? Are they scattered? Second, it defines the relationships between those stored values. Is there a sequence, a hierarchy, a network? And third, based on that organization and relationship, it defines the operations that can be efficiently performed on the data within that specific structure. What can you do with the data, and how fast can you do it? It's really the blueprint for how data behaves and how you can effectively interact with it.
Okay. And the most fundamental one, which, as you said, Python calls a list, but is conceptually an array in many other languages like Java or C++. What defines an array at its core?
Right. An array is probably the most fundamental data structure after primitive types. It stores a collection of values, where each value is referenced or accessed using an index, usually a number starting from 0 or sometimes a key. A good analogy is to think of an array as a set of train cars, all linked together in a line. Each car is numbered sequentially 0, 1, 2, and so on, and each car holds some data inside it.
Like compartments.
Exactly, compartments. And interestingly, strings, which just look like text, are often implemented under the hood as arrays of characters.
Now, there's a difference sometimes between languages, right? Like, can arrays hold different types of data?
That's a key difference. In languages like Java or C++ or Swift, arrays are often homogeneous. That means they can only contain values of the same data type. You declare an array of integers or an array of strings, and that's all it can hold. Python lists, on the other hand, are heterogeneous. You can mix numbers, text, other lists, objects, whatever you want, all within the same list.
How does Python manage that if arrays are usually about storing things of the same size next to each other?
Python pulls a clever trick. Python lists achieve this flexibility by typically allocating contiguous memory, not for the actual data values themselves, which can be of varying sizes, but for references or pointers to where the actual values are stored elsewhere in the computer's memory. Since all these pointers' memory addresses are the same size, figure 64 bits, Python can store the pointers contiguously, preserving the core advantage of contiguous memory for accessing the references quickly, while still allowing the referenced objects themselves to be of different types and sizes stored elsewhere.
That's clever. So it keeps the benefits of contiguous storage for the pointers. And that contiguous memory aspect is really key to an array's efficiency for certain operations, isn't it?
Absolutely fundamental. Arrays, or the underlying structure of Python lists, are contiguous data structures. This means their elements, or at least the pointers to their elements in Python's case, are stored in blocks of memory directly next to each other, without any gaps in between. This contiguous nature is the foundation of their efficiency for certain operations. Why? Because instead of needing to store the memory address for every single element individually, the array only needs to store the memory address of the very first element. This is often called the base address. Then the memory address of any other element, say the element at index I, can be calculated directly and very quickly using simple arithmetic base address plus index element size.
Direct calculation, no searching needed.
Exactly. No need to follow pointers or search. It's a direct jump using math. This direct calculation is what makes certain array operations incredibly fast.
Okay, so let's break down the common operations you'd perform on arrays or Python lists and analyze their costs, their big O efficiency, based on this contiguous structure. Starting with the big one, accessing or reading elements by index, like my listing.
This is where arrays absolutely shine. As we just discussed, when you want to access an element using its index in I, the computer can use that formula, base address plus I element size, to directly calculate its precise memory location. There's no need to iterate through the list or follow a chain of pointers. This makes accessing or reading by index an O1 constant time operation.
O1, super fast.
Incredibly fast.
Yeah.
Regardless of how large your list is, 10 elements or 10 million, accessing an element at a known index takes essentially the same, very small, fixed amount of time.
Like directly jumping to a specific numbered seat in the theater?
Perfect analogy. If you know the seat number, the index, you can go straight there.
Yeah.
And this direct calculation, by the way, is also why you get index out of bounds errors if you try to access an index that doesn't exist. If the calculated memory address falls outside the allocated block of memory for the array, the system rightly says, nope, can't read or write there.
Right. Makes sense. Okay, O1 access is the superpower. What about searching for a specific value within an array? Not by index, but finding if, say, the number 42 is in the list.
For searching for a value in an unsorted array, the most efficient general approach you have is linear search. You have no choice but to start at the beginning and check each item sequentially. Is this 42? No. Is this 42? No. Until you either find it or you reach the end of the list. As we established earlier, this results in ON, linear time complexity, in the worst-case scenario, where the values at the very end are not present at all. The time taken grows linearly with the number of elements.
And in Python, using the in operator, like if 42 in my list, would that be ON?
Yes, typically the in operator for Python list performs a linear scan under the hood, so its complexity is ON. Of course, if the array were already sorted, you could leverage the much faster O log n binary search, but sorting itself, as we noted, adds its own computational cost up front.
Right. Okay. Access is O1, search is ON usually. Now, what about inserting a value into an array? This seems like it might mess with that contiguous structure, especially if you want to insert it at a specific index, not just stick it on the end.
It definitely does. This is where arrays start to show their weakness. For a true insertion at a specific index I, that is in the very end, think about what needs to happen to maintain that contiguous block and keep all the later elements correctly indexed. To make space for the new element at index I, all the elements currently at index I and onwards, I plus 1, I plus 2, must be physically shifted one position to the right in memory.
Shifting everything over, that sounds expensive.
It is, especially for large lists. In the worst-case scenario, if you're inserting a new element at the very beginning of the list, index 0, every single existing element needs to be shifted one spot over. This makes true insertion an ON, linear time operation. The time it takes is proportional to the number of elements that need to be shifted, which can be up to n. This is a major drawback of arrays for applications that require frequent insertions into the middle or beginning of a collection.
Ouch. Okay, so inserting in the middle is slow. But what about just adding a new element to the very end? That feels different, maybe easier. Is that still ON?
That is different and generally much better. Most dynamic array implementations, like Python lists, use a clever strategy here. They often pre-allocate a bit more memory than is immediately needed when the list is created or resized. So when you append an item using .append, if there's still available space in that pre-allocated block, the operation is incredibly fast. It just writes the new value, or its pointer, into the next empty slot and updates the size counter. That's just O1.
If there's room, it's O1. But what if the pre-allocated space is full?
Right. If the allocated block is full when you try to append, then the list must be resized. This is a more expensive operation. A new, larger block of memory is requested, often double the previous size, and all the existing elements from the old block have to be copied over to this new, larger block. This resizing operation itself is an ON operation because you have to copy n elements.
So appending is sometimes O1 and sometimes ON. How do we classify that?
This is where the concept of amortized analysis comes in. While individual resize operations are costly, they happen relatively infrequently if the list grows using a good strategy, like doubling capacity, 0, 4, 8, 16, 32 elements. Because these expensive ON resizes are spread out over many cheap O1 appends, the average cost of appending, when amortized over a large number of append operations, works out to be effectively amortized O1 constant time.
So on average, appending is considered O1. That's good.
Yes, it's a very efficient design and practice for adding elements to the end.
And what about extending a list, like using .extend to add all elements from another list?
Extending a list essentially performs a series of append operations, one for each element in the list being added. So if you're sitting with a list that contains k elements, the efficiency is roughly, it scales linearly with the number of elements you are adding.
Makes sense. Finally, deleting a value from an array. Is that similar to the insertion problem? Do things need to shift?
Yes, very similar to insertion in terms of cost and mechanics, unfortunately. When you delete an element from an array, say at index Y, you create a gap. To maintain the contiguous structure and ensure subsequent elements have the correct indices, all the elements after the deletion point I plus 1, I plus 2 must be physically shifted one position to the left to close that gap.
Shifting again.
Shifting again. And again, the worst case scenario is deleting the very first element, index 0, of a large list, which requires shifting every single subsequent element one position to the left. This makes deletion, like insertion, generally an ONT linear time operation. Another significant weakness for arrays in scenarios requiring frequent removals from anywhere other than the very end.
Okay, so summing up arrays, or Python list, fantastic, O1 for reading writing if you know the index, good, amortized O1 for appending to the end, but potentially slow, ON for searching if unsorted, inserting in the middle, and deleting from the middle. Given those limitations, especially the ON cost for frequent insertions and deletions, does that mean we're just stuck with slow operations in those cases? Or is there another way to structure our data, another type of data structure that might optimize for those specific operations, even if it means sacrificing something else, like that fast O1 index access?
Precisely. This inherent limitation of arrays, the cost associated with shifting elements to maintain contiguity during insertions and deletions, is exactly what motivates the design and use of other data structures. We look for structures that might offer better performance for those specific operations. A prime example of such a structure is the linked list. It's designed with a fundamentally different underlying organization, specifically to make certain types of insertions and deletions more efficient compared to arrays, particularly if you don't absolutely need that constant-time random access by index. It's all about tailoring the structure to the problem's primary needs and access patterns.
Okay, so let's build this alternative, the linked list. What exactly is it? How is it structured differently from an array?
A linked list is also a linear data structure, meaning it represents a sequence of items. But unlike arrays, its elements are not stored contiguously in memory. Instead, each element in the list is contained within a separate object, and this object is called a node. Each node object typically holds two crucial pieces of information. First, the actual data you want to store, like a number, a string, or any object. Second, a reference or pointer to the next node in the sequence.
So each node points to the next one in the chain.
Exactly. The list itself is formed by linking these nodes together like beads on a string, where each bead has an arrow pointing to the next bead. The linked list data structure itself usually only needs to keep track of one thing, a reference to the very first node in the list, which is called a head. The chain continues until you reach the very last node, called a tail. The tail node is special because its next node reference doesn't point to another node. It points to none, or null, signaling the end of the list.
Like a treasure hunt, you start with the first clue, the head, which tells you where the treasure is, A and D, where the next clue is hidden. Each clue you find gives you another piece of treasure and the location of the next clue, until you find a clue that says, no more clues. That's the tail, the end of the hunt.
That's a perfect analogy. It captures the sequential, linked nature. You can only get to the next item by following the link from the current item. And this structure highlights a key concept. Nodes are often self-referential objects. The node class definition contains an attribute, next node, that holds a reference to another object of the same type, node.
Are there different kinds of linked lists?
Yes. The basic type we're describing, where each node only points forward to the next node, is called a singly linked list. That's what we'll focus on. There are also doubly linked lists, where each node has two pointers, one to the next node and another to the previous node. This allows you to traverse the list forwards and backwards, offering more flexibility for certain operations, but it comes at the cost of using slightly more memory per node to store that extra backward pointer.
Okay, let's stick with this singly linked list implementation in Python for now. We'd need a node class and a linked list class, right? And let's look at the big O implications of its key operations. How do we check if it's empty or get its size?
Right. You'd have a simple node class, maybe with an init method that takes data and optional next node, defaulting to none. Then you'd have a linked list class whose init method simply sets its head attribute to none, representing an empty list initially. The asEmpty method is very simple. It just checks if self.head is none. This is a direct check, taking the same amount of time regardless of list size. So isEmpty is an O1 constant time operation.
Okay, O1 for empty check. What about getting the size? Is it like Python's built-in listlen, which is O1?
No, this is a major difference. Unlike Python's built-in list, which stores its size, a basic linked list usually only stores a reference to the head. To find out how many nodes are in the list, you must traverse the entire list. You start at the head, initialize a counter to 0, then you follow the next node pointers from one node to the next, incrementing the counter for each node you visit until you reach the end, where next node is none. Because you have to visit every node in the worst case, calculating the size of a linked list is an ON linear time operation. It takes longer for longer lists.
ON for size. That's way different from O1 for erase Python lists. Okay. What about adding elements? We said linked lists might be better here. Let's look at prepending adding a new node right at the head of the list.
Yes. Adding to the front, often called add or prepend, is where linked lists demonstrate a key advantage over arrays. Here's how it works. You create a new node containing the data you want to add. Then you set the new node.nextNode reference to point to whatever the current self.head of the list is. This links the new node to the rest of the list. Finally, you update self.head to point to this new node, making it the new first node.
So just creating a node and shuffling a couple of pointers around.
Exactly. It involves only a few constant time pointer reassignments. Crucially, no existing elements need to be shifted or copied, unlike inserting at the front of an array. Therefore, adding a node to the head of a linked list is an O1 constant time operation. This is a significant performance gain over arrays if your application frequently adds items to the beginning of a sequence.
Well, one, add up front. Nice. Okay, what about just representing the list as a string, maybe for printing, like implementing REPL?
To get a string representation of the entire list, you again need to see all the data. So you have to traverse every node from the head to the tail. You'd start at the head, collect its data, move to the next node, collect its data, and so on, building up the string representation as you go. Since you have to visit every node, generating the string representation is also an ON linear time operation.
Okay, ON to print it all out makes sense. Now, what about searching for a value? Using a search key method to find if a particular piece of data exists in the list. Is it better or worse than arrays?
For searching for a specific value key, a linked list behaves very similarly to an unsorted array. You have no way to jump directly to a specific position. You must start at the head and traverse the list node by node, comparing the data in the current node to the key you're looking for. You continue this until either a match is found, you return true or the node, or you reach the end of the list, none, without finding it, you return false. This sequential traversal means that searching in a singly linked list is an ON linear time operation in the worst case. Key is at the end or not present. Linked lists are inherently poor at random access or searching compared to a sorted array with binary search.
Okay, ON search, same as an unsorted array. Now, the other potential advantage area, inserting or removing a value at a specific index or removing a node with a specific key. You said O1 for adding at the head, but what about elsewhere? It feels like you'd still have to find the spot first, which sounds like ON traversal.
You've hit the nail on the head. That's the crucial caveat. Let's consider insert data, index where index 0 or remove key. To insert at a specific index, other than 0, you must first traverse the list from the head until you find the node just before the desired insertion point. Let's call it the previous node. Finding this previous node takes, on average, ON time. Once you have found the previous node, the actual insertion is fast. You create the new node, set new node.next node to previous.next node, and then update previous.next node to point to new node. This pointer shuffling is O1.
But finding the spot took ON.
Right. Similarly, for remove key, you have to traverse the list to find the node containing the key, and you also need to keep track of the previous node as you go. Finding the node in its previous node takes ON time in the worst case. Once found, the actual removal is just bypassing the node. You set previous.next node to point to current.next node, where current is the node being removed. The pointer change is O1.
So the actual unlinking is fast, O1, but getting there is slow, ON.
Exactly. Therefore, the overall complexity for insertion or deletion at an arbitrary position, or removing by key, in a singly linked list is dominated by the initial traversal step, making it ON linear time.
So the O1 insertion deletion benefit is really only if you already have a direct reference to the node before where you want to insert delete, like inserting deleting at the head.
Precisely. The O1 performance applies mainly to operations at the very head of the list, or potentially at the tail if you maintain a separate tail pointer and are doing simple append removals there, and maybe using a doubly linked list for tail removals. But for operations in the middle based on index or key, the ON search traversal cost dominates.
Okay, that clarifies the trade-offs significantly. So what's the practicality of linked lists then? They're clearly fantastic for learning fundamental data structure principles, pointers, nodes, traversal. But given these performance characteristics, where do they actually fit in real-world programming compared to, say, Python's highly optimized built-in list?
That's a really fair question about practicality. While linked lists are invaluable as a teaching tool for understanding how data can be structured non-contiguously and how pointers work, you're right, they are actually less common in day-to-day general-purpose programming, especially in languages like Python that provide such powerful and optimized built-in list implementations. Python's list handles dynamic resizing, memory management, and provides that amortized O1 append very efficiently, making it the default choice for sequential data most of the time.
So mostly for learning, or are there specific niches?
There are definitely niches. Linked lists are incredibly valuable as the underlying structure for implementing other abstract data types. For example, queues, first in, first out, and stacks, last in, first out, are often implemented using linked lists because they primarily involve efficient insertions and deletions at one or both ends, head tail, which linked lists excel at O1. They can also be useful in specific application scenarios where you have very frequent insertions or deletions happening right at the beginning or end of a sequence, and you rarely, if ever, need to access elements by index randomly. Think perhaps of managing a list of tasks where you constantly add new tasks to the front or process tasks from the front. And many programming language standard libraries do provide their own highly optimized linked list implementations, like Java's linked list, for developers who need precisely those performance characteristics. So they are definitely used, just perhaps less universally than dynamic arrays for general sequence storage.
Got it. Learning tool, building block for other structures, and useful in specific scenarios focused on head-tail operations.
Okay, that's a great overview of arrays versus linked lists. Now let's bring it all back to algorithms. Specifically looking at more advanced algorithms, we need to tackle sorting, because we established earlier that super fast algorithms like binary search demand sorted data. So how do we efficiently sort a list in the first place? Let's look at merge sort.
Yes, sorting is fundamental, and merge sort is a classic, elegant, and efficient sorting algorithm. It beautifully demonstrates a powerful algorithmic strategy called divide and conquer.
Divide and conquer. We heard that with binary search too, in a way. How does it apply to sorting?
It's a core paradigm. The strategy involves 3 steps. 1, divide, break down the large, complex problem, the unsorted list, into smaller, more manageable subproblems. Keep breaking them down until they become trivial to solve. 2, conquer, solve the trivial subproblems. 3, combine. Combine the solutions to the subproblems in a way that solves the original large problem. How does merge sort actually do that with a list of numbers? Can we use that analogy you liked earlier? Imagine our teacher has a massive unsorted stack of graded exam papers she needs in alphabetical order. Instead of doing it all herself, she splits the stack exactly in half and gives each half to a student assistant.
Okay, good start.
Those students then split their halves and pass them on to other assistants. This keeps happening down the chain until individual assistants have just 1 or maybe 2 papers.
Right, the trivial case.
They can easily sort their tiny pile of 1 or 2 papers, then they pass their sorted mini pile back up to the person who gave it to them. That person now has 2 small, already sorted piles. Their job is to merge those 2 sorted piles into one slightly larger, still sorted pile.
The combine step.
Exactly. And this merging process continues back up the chain. At each level, 2 sorted subpiles are merged into a larger sorted pile until finally the original teacher gets back 2 large sorted halves, merges them one last time, and voila, the entire stack is perfectly sorted.
That's a perfect analogy. It captures the essence beautifully. Let's map it to the algorithm steps. 1, divide. Recursively split the unsorted list or array exactly in half, creating 2 sublists. You keep doing this until you are left with sublists containing only a single element. A list with 1 element is, by definition, already sorted. That's a base case for the recursion. 2, conquer. Each of these single element lists is trivially sorted. The conquering step is essentially reaching this base case. 3, combine. This is the crucial merge step. Start merging these sorted single element lists back together. When you merge any 2 sorted sublists, you do it intelligently to create a new, larger list that is also sorted. You repeat this merging process, combining pairs of sorted lists into larger sorted lists until you have merged everything back into one complete, fully sorted list. The merging part sounds key. How does that work efficiently? The merge operation itself is quite clever. If you have 2 already sorted sublists, say left and right, you can create a new sorted merge list in linear time. You use 2 pointers, one starting at the beginning of left I and one at the beginning of right j. You compare lefting and right j. Whichever is smaller gets appended to the merge list, and you advance only the pointer for the list that element came from. You repeat this comparison until one of the lists runs out of elements. Then you just append all remaining elements from the other list, since they must be larger than everything already merged and are already sorted amongst themselves. This merge takes time proportional to the total number of elements in both lists.
Okay, that makes sense. Let's look at its implementation on arrays using Python lists. How would the code structure look with the main function and those split and merge helpers?
Right. The top-level function, let's call it merge sort, list to sort, would look something like this. First, the base case. If len list is sorted 1, the list is already sorted or empty, so just return list to sort. If not the base case, then the divide step. Call a helper function, say split list to sort, which returns 2 new lists, left half and right half. Then the conquer step, recursive calls, call merge sort on each half, left merge sort left half and right merge sort right half. This continues recursively until the base case is met for all subproblems. Finally, the combine step. Call the merge helper function to combine the now sorted left and right sublists, return merge left-right.
And how would those helpers work, especially split using Python lists?
The split list-to-sort helper function is straightforward with Python lists. It calculates the midpoint index, usually lens list to sort 2. Then, crucially, it uses Python's convenient list slicing. It returns list-to-sort.midpoint as the left half and list-to-sort midpoint as the right half. Slicing automatically creates new lists containing the appropriate elements. The merge, left-right, helper function would implement that pointer comparison logic we just discussed. Create an empty merge list, use I and j pointers for left and right, loop while both I and j are within bounds, compare lefty and right j, append the smaller one to merge list, increment the corresponding pointer. After the loop, append any remaining elements from left or right, finally return the merged list.
Okay, that recursive structure with splitting and merging seems clear. Now, complexity. This sounds like it should be that efficient ON log n quasi-linear time we talked about earlier, but you hinted there might be a crucial Python gotcha here specifically because of that list slicing in the split function. Does that affect the actual time complexity in this implementation?
You're very perceptive. Yes, there's a subtle but important detail here regarding the performance of this specific Python implementation using slicing. Conceptually, the merge sort algorithm itself, regardless of implementation, performs O log n levels of division and merging, and the merging work at each level takes ON time in total. This leads to the famous ON log n time complexity overall. It's known for this reliable performance. However, in our specific Python implementation, using list-to-sort.midpoint and list-to-sort-midpoint, the split function relies on list slicing, and Python's list slicing operation is not O1. Creating a slice requires copying elements into a new list. The time complexity of slicing is actually OK, where k is the size of the slice being created.
So making those slices takes time proportional to the size of the slice.
Exactly. In our split function, k can be up to n2. This means that our Python implementation split step adds an extra OK cost at each of the O log n levels of recursion. When you combine this OK slicing cost per level with the ON merge cost per level, the total runtime of our specific Python implementation using slicing becomes roughly OKN log n, or arguably closer to ON log n if we are careful with analysis. But the key point is that the slicing adds overhead compared to implementations that avoid it.
So it's less efficient than a true ON log n. How would you avoid the slicing overhead?
A more optimized implementation, often seen in languages like C++ or Java, or even possible in Python, would avoid creating new lists during the split. Instead, it would pass the original list along with start and end indices to define the subarray being worked on recursively. The split step then just involves calculating the midpoint index, not creating new data structures. This avoids the OK slicing cost and achieves a runtime closer to the theoretical ON log n.
Okay, that's a critical implementation detail. Good to know. What about the space complexity for merge sort on arrays? How much extra memory does it need?
Merge sort, even the version using indices, generally has an ON, linear space complexity.
ONN. Why linear? It seems like it creates lots of sublists recursively.
That's true, but they aren't all necessarily held in memory simultaneously if implemented carefully. However, the primary space requirement usually comes from the merge step. When you merge two sorted sublists, left and right, you typically need to create a new temporary list, merged list, to store the sorted result. In the worst case, this temporary list needs to be large enough to hold all n elements from the original list. While you can sometimes do in-place merges, they are much more complex to implement correctly. The standard simpler merge sort requires auxiliary space proportional to the original input size, n, for that merge buffer. Therefore, its space complexity is typically O.
O in space. Okay. So that's merge sort on arrays with the Python slicing caveat. But what about applying merge sort to linked lists? This must be fundamentally different again because linked lists lack that O1 index access and easy slicing. How would that work?
It is indeed different, and it really highlights again why the underlying data structure deeply influences how you implement an algorithm and what its actual performance is. Linked lists, as we know, lack direct random access, ON, to get to the ith node, and don't have a simple slicing operation like arrays. This means operations that are easy with arrays, like splitting the list exactly at the midpoint, become more cumbersome and potentially less efficient with linked lists.
So how would the merge sort linked list function work? Is the overall divide, conquer, combine idea the same?
Yes, the top-level recursive logic of merge sort, linked list, is conceptually very similar to the array version. It handles the base cases, empty list or list with one node is already sorted. It calls a split link a list function to divide the list into two halves. It makes recursive calls, left merge sort left half, and right merge sort right half. And finally, it calls a merge linked list left right function to combine the sorted sublists. The differences lie entirely within the implementation of the split and merge helper functions for linked lists.
Okay, let's focus on that split list function for linked lists. How do you split a linked list in half without slicing or O1 index access?
This is where it gets tricky. The split function for linked lists needs to 1. Handle the base cases, empty your single node list. 2. Find the midpoint node. How? It usually has to first calculate the size of the list, which we know is ON. Then it needs to traverse from the head size 2 steps to find the node at the midpoint. Let's say we add a new helper method to our linked list class. Node each index. 3. Once the mid node is found, the actual split happens by manipulating pointers. The original linked list becomes the left half. A new linked list is created for the right half. The head of the right half is set to midnode.next node, the node after the midpoint. And crucially, the connection between the two halves is severed by setting midnode.next node to weasel none.
Yeah.
This effectively creates 2 distinct independent linked lists. Whoa! So finding the midpoint requires that new helper, node index. How efficient is that on a linked list?
There's the rub. The node index helper method, because it's operating on a linked list, must traverse the list from the head, stepping through next node pointers, index number of times until it reaches the desired node. This traversal makes node EA index an ON linear time operation, specifically O index, which can be up to N2. This is a significant overhead compared to the O1 excess of arrays.
Okay, and just to find the split point, and how does the merge left-right function work for linked lists? Is it also pointer manipulation? Yes, the merge operation for 2 sorted linked lists, left and right, also involves careful pointer manipulation, but it's conceptually similar to the array merge. You might create a temporary dummy head node for the merged list to simplify the logic of adding the very first node. You'd keep a current pointer, initially pointing to this dummy head. Then you iterate while both left.head and right.head are not none. You compare the data in the left.head node and the right.head node. Whichever node has the smaller data gets linked to current.next node. You then advance the head pointer of the list that node came from, e.g. left.head.next node. And you also advance the current pointer, current.next node. After the loop finishes, one list is exhausted, you link the remaining portion of the other list onto the end, current.next node, remaining list.head. Finally, you return dummyhead.next node, which is the true head of the fully merged sorted linked list. This merge process itself is still efficient, roughly ON time, where N is the total number of nodes being merged, because you process each node once.
Okay, the merge seems efficient, ONN, but that's split. Finding the midpoint took ON because of the traversal needed by node NEA index. How does that impact the overall time complexity of merge sort on a linked list?
That ON cost within the split function is the bottleneck for the linked list implementation. Because split, which includes the OA no index call, is performed at each of the O log n levels of recursion, the work done just to split the list adds a substantial ON overhead at each level.
So it's like ON work for splitting plus ON work for merging, done O log n times.
Exactly. This makes the linked list implementation's total runtime approximately ON log n due to the split overhead. Similar in big O terms to the conceptual algorithm, but likely with larger constant factors making it slower in practice than an optimized array version that avoids ON splits. There are slightly more advanced ways to find the midpoint of a linked list in ON time using a fast, slow pointer technique without needing the size first, but the split operation fundamentally involves traversal.
So the key insight remains. While merge sort's core divide and conquer idea is the same, its practical efficiency heavily depends on the underlying data structure's strengths and weaknesses.
Precisely. The linked list's inherent lack of O1 random access makes implementing algorithms like merge sort, which benefit from easy midpoint finding, less performant than an optimized array-based version where finding the midpoint index is O1 and splitting, if done via indices, is also O1. It really drives home the importance of choosing the right data structure for the algorithms you intend to run on it.
That's a fantastic deep dive into merge sort and how it interacts with the different data structures. Okay, let's broaden our view now and do a quick comparison of sorting algorithms. Because we've seen big O notation is powerful, but you mentioned constant factors matter, and sometimes the average case is more important than the worst case. It doesn't always tell the whole story about practical, real-world performance.
Indeed. Big O describes the asymptotic growth rate, how it scales as N gets huge. But for actual wall clock time on realistic inputs, those constant factors, how fast the individual repeated operations actually are on the hardware, can significantly impact which algorithm is faster in practice. Let's maybe start with one that illustrates the absolute worst possible scenario, just for contrast. Bogosort.
Bogosort, that sounds deliberately bad, like a joke algorithm. How does it even work?
It basically is a joke algorithm used for educational contrast. It works by randomly shuffling the list elements, then checking if the list happens to be sorted. If not, it shuffles again and again and again.
It just keeps shuffling randomly until it gets lucky.
Exactly. It's purely a matter of luck and makes absolutely no intelligent progress towards a sorted solution. Its efficiency is an astronomical ONN, on average, or even worse depending how you define it, essentially related to factorial time. For even a moderately sized list, say 8 or 10 items, it could take thousands, millions, or practically infinite attempts to randomly stumble upon the sorted order. For large lists, it's completely, utterly unusable.
Okay, so real-world use. Absolutely none. Good for demonstrating how not to sort.
Precisely. Now, let's move to something slightly more sensible, but still quite slow. Selection sort.
Selection sort. I think I remember this one. How does it work?
Selection sort works by iteratively scanning through the list. In each pass, it finds the smallest element in the unsorted portion of the list and swaps it with the element at the beginning of the unsorted portion. Effectively, it builds up the sorted list from left to right, one element at a time.
So in each pass, it selects the minimum and puts it in place.
Correct. It always makes progress, unlike Bogosort. However, finding that minimum element in the unsorted portion requires scanning that portion, which takes ON time initially, then ON1, ON2, and so on. You do this n times. This results in an overall efficiency of ON2 quadratic time.
ON2. So like those basic nested loop algorithms, slow for large N.
Very slow for large data sets. To sort, say, 10,000 numbers, selection sort might take several seconds. To sort 1,000,000 numbers, it could easily take hours or even time out your system. Its main advantage is simplicity. It's relatively easy to understand and implement. So it's occasionally used for very small lists where that simplicity might outweigh the poor performance, but rarely otherwise.
Okay, ON2 is generally too slow. Now let's talk about the algorithms often considered the real-world champions, starting with Quicksort. How does that one work, and what's its performance profile like? It's another divide and conquer, isn't it?
Yes, Quicksort is another classic divide and conquer algorithm. But it works differently from merge sort. It starts by picking an element from the list, which is called the pivot. The choice of pivot is important, as we'll see. Then, it partitions the rest of the list into two sublists based on the pivot. One sublist contains all elements less than or equal to the pivot, and the other contains all elements greater than the pivot. The pivot itself ends up in its final sorted position between these two sublists. Finally, it recursively applies quicksort to these two smaller, independent sublists.
So merge sort splits first, then merges sorted halves. Quicksort partitions around a pivot first, then sorts the partitions.
Exactly. The work is shifted. Now, quicksort's performance is interesting because it varies significantly depending on how well the pivot divides the list. The best case, an average case with good pivot selection, is ON log n. This happens when the pivot consistently divides the list into roughly equal halves at each step.
ON log n, same as merge sort's ideal. But quicksort has a dark side, a worst case.
It does. Quicksort's worst case is ON2, the same as selection sort.
ON2, how does that happen?
This occurs if you consistently make bad pivot choices. For example, if the list is already sorted or reverse sorted, and you always pick the first or last element as the pivot. In this situation, the pivot doesn't divide the list well at all. One partition will contain N1 elements, and the other will be empty. The recursion becomes very unbalanced, essentially degrading to repeatedly finding the min-max element, which leads to ON2 performance.
So it can be as bad as selection sort in its worst case, but despite that, it's still considered a champion often. Why is that?
Because of its average case performance and its performance in practice. By choosing pivots more strategically, for example, picking a random element as a pivot, or using a median of 3 approach, picking the median of the first, middle, and last elements, you can make the probability of hitting that exact worst-case scenario extremely low for typical inputs. With good pivot selection, Quicksort's average performance is reliably ON log n.
And how fast is it in practice?
Very fast. For sorting, say, 10,000 numbers, a well-implemented Quicksort might take well under a second, maybe around 0.5 seconds in some tests. For 1,000,000 numbers, it might take around 10-11 seconds. Because the operations involved in this partitioning step are often very efficient on actual hardware, involving swaps and comparisons in place, Quicksort is frequently one of the fastest general-purpose sorting algorithms in practice for arrays. It's widely used in standard libraries.
Okay, fast on average, ON log n, but with a potential ON2 lurking if you're unlucky or pivots poorly. And then there's merge sort, which we just went deep on. Let's recap its efficiency compared to Quicksort.
Right. Merge sort, as we explored, also uses divide and conquer by splitting the list in halves recursively down to single elements, then merging those sorted halves back together. Its key advantage and difference from quicksort is that its efficiency is always O(n) log n, regardless of the input data. It doesn't suffer from a pathological worst-case scenario like quicksort because its splitting strategy, halving the list, is inherently balanced. It always divides the work evenly.
Always O(n) log n. That sounds safer. How does its practical performance compare?
In terms of practical performance on arrays, merge sort is usually very competitive with quicksort, but often slightly slower on average. For those 10,000 numbers, it might take around 0.8 seconds compared to quicksort's 0.5. For 1 million numbers, maybe 15 seconds compared to quicksort's 11.
Okay, so this brings us right to that big, maybe paradoxical question. Quicksort versus merge sort. Quicksort's worst case is O(n)2, while merge sort is guaranteed O(n) log n. Yet you're saying quicksort is often preferred or more commonly used in practice. Why would that be? That seems counterintuitive.
It is a classic paradox in algorithm analysis, and it perfectly highlights that big O notation, while essential for understanding scaling, doesn't capture the entire picture of real-world performance. Remember, big O only describes how many times an operation is performed, the growth rate, not how long each individual operation actually takes, the constant factors. The constant factor operations involved in quicksort's main loop, the partitioning step, which usually involves comparing elements and swapping them within the existing array in place, are generally very fast and efficient on typical computer hardware, good cache locality, etc. The constant factor operations in merge sort's main loop, the merging step, often involve comparing elements and then copying them to a new auxiliary array. This copying step can introduce overhead, making the individual operations slightly slower in practice than quicksort's in-place swaps.
Ah, so even though both might do roughly O(n) log n operations, the operations quicksort does are often lighter or faster on the CPU.
Exactly. Quicksort tends to have smaller constant factors in its runtime equation, making it perform better on average for typical hardware and datasets, despite its theoretical worst-case complexity.
That's fascinating. So big O is critical for understanding scaling and avoiding catastrophes like O(n)2 on average. But sometimes you need to look beyond it at the constant factors and practical implementation details to choose the absolute fastest algorithm for a specific context.
Precisely. It's a great example of where theoretical analysis meets practical engineering. You need both perspectives. Quicksort's average case speed often wins out in practice, which is why it's so common. But merge sort's guaranteed O(n) log n makes it a safer choice in situations where that worst case guarantee is critical, or for external sorting, or sometimes for linked lists where its merging is more natural.
That makes so much sense. It's not just about the number of steps, but how heavy each step feels to the computer. Okay, let's tie this all together now. Because we started this whole conversation about sorting algorithms for a very specific reason, achieving efficient searching. This is the grand payoff, isn't it? The significant effort we put into sorting a list, often using quicksort or merge sort, both typically O(n) log n, is primarily done to unlock the power of that highly efficient binary search.
Exactly. This is where the rubber meets the road, connecting sorting and searching. Let's quickly revisit linear search. Its efficiency is O(n). It's your only practical option if you have an unsorted list. Remember that example? Searching for 100 specific names in a 100,000 name unsorted list. It might take a measurable amount of CPU time, perhaps around 0.9 seconds in a hypothetical test. Fine for one search, maybe, but what if you do thousands?
Yeah, 0.9 seconds per 100 searches adds up fast if you're doing it constantly. But now, thanks to our sorting efforts, which took, say, O(n) log n time once up front, we can revisit binary search.
Right. Binary search's efficiency is that fantastic O log n. But it absolutely requires a sorted list. Now, if you search for the same 100 names in that 100,000 name list, but now it's sorted after a one-time sorting cost, the search time drops dramatically. Instead of 0.9 seconds, maybe it takes only about 0.25 seconds total for all 100 searches.
Wow, from 0.9 seconds down to 0.25 seconds for the same task, just because the list was sorted first. That's nearly a 4x speed up in this example.
It is. And this difference becomes exponentially more pronounced with larger data sets and a higher volume of search queries. That initial cost of sorting the data, O(n) log n, is often a worthwhile one-time investment if you plan to perform many searches afterward. Each subsequent search benefits massively, running an O log n time instead of O(n).
So it's a perfect real-world example of choosing the right combination of tools, algorithms, and data structures for your specific problem based on its needs and patterns of use, like sort once, search many times.
Absolutely fundamental. It's about understanding the trade-offs and optimizing for the most frequent or critical operations required by your application.
Well, this has been an incredible journey. We've covered a tremendous amount of ground in this deep dive, from the fundamentals right through to practical comparisons. Let's maybe try and recap the main points of our journey.
We really did cover a lot. We started by defining what algorithms are, emphasizing they're more than just steps. They represent this body of proven, efficient knowledge for problem solving, honed by computer science over decades. And we talked about why understanding them is so fundamental to effective programming and algorithmic thinking.
Right. Then we explored those critical metrics of time and space complexity, how we measure efficiency, and we introduced Big O notation as that universal language for evaluating how algorithm performance scales, acting as that crucial early warning system for whether your code will handle large inputs gracefully or grind to a halt.
We took a deep dive into search algorithms, contrasting the simple but O(n) linear search with the incredibly fast O(n) binary search, really hammering home the mechanics, the real-world applications, and that critical precondition of needing sorted data for binary search.
We then delved into the world of data structures, examining the efficiency of common operations on arrays, using Python lists as our practical example. We saw their strength, that amazing O(n) random access, but also their weaknesses, like the O(n) cost for insertions and deletions in the middle due to element shifting.
And we even conceptually built our own linked list from scratch, highlighting how its different node and pointer structure leads to different trade-offs. O(n), insertion deletion at the head, but O(n) for size, search, and middle operations, making it suitable for different use cases than arrays.
Yeah, that comparison was really illuminating. Finally, we brought it all together by implementing and comparing advanced sorting algorithms. We looked closely at merge sort, understanding its guaranteed O(n) log n time, but also its O(n) space complexity, and the implementation nuances with Python's list slicing or linked list traversal affecting practical performance.
And we compared merge sort to other sorts, like the disastrous Bogosort O(n), the simple but slow selection sort O(n)2, and the often practically fastest quick sort average O(n) log n, but worst case O(n)2. That comparison really highlighted the difference between theoretical worst case big O and average case practical performance driven by constant factors.
And we didn't forget recursion. We touched on that powerful, sometimes elegant programming paradigm, discussing base cases, recursive cases, and the practical considerations in Python regarding stack depth and the lack of tail call optimization impacting space complexity.
Absolutely. And the overarching goal of this whole deep dive really wasn't for you listening to memorize every single line of code or every big O complexity for every possible algorithm variation. It was much more about arming you with the conceptual tools for algorithmic thinking, to help you understand that algorithms and data structures aren't just abstract academic topics. They are the invisible engines, the fundamental building blocks, powering virtually all the software you use every day. Knowing how they work internally, understanding their strengths, weaknesses, and performance characteristics allows you to make better design decisions, build more robust, more scalable, and ultimately more performant solutions in your own work. It's about choosing the right recipe and the right kitchen tools for the meal you're trying to prepare.
Perfectly put. It's about informed choices. And maybe to leave you, our listener, with a provocative thought to mull over as you continue your learning journey. Given how dramatically data volumes continue to scale in our modern world, think petabytes, exabytes, consider a complex problem you encounter or can imagine. Maybe it's efficiently organizing and searching a massive digital photo library with potentially millions or billions of images, each with metadata. Or perhaps designing the core system for ultra-fast product searches on a global e-commerce site, handling millions of unique items and potentially millions of concurrent user queries per second. If you had to design the underlying architecture for such a system, which specific algorithm and data structure choices would you prioritize to achieve the best possible performance for those specific needs? How would you carefully balance the trade-offs between speed, memory usage, and maybe the frequency of data updates or insertions? And thinking back to quicksort versus merge sort, would you lean towards an algorithm that is consistently efficient across all inputs, or one that's generally faster on average but carries the risk of a potentially worst case scenario? What factors would drive that decision?
That's a great thought experiment. The world of algorithms and data structures is vast, deep, and endlessly fascinating. There's always more to learn and explore. So keep exploring, keep questioning the trade-offs, and keep designing better solutions. Happy coding.